Okay, so I want to discuss with you question number 5, part A, because I was not able to explain it to you earlier this morning. This is something to do with tangent line approximation. So if you read the problem, it says estimate the radius of the balloon when t equals 5.4. So we're basically looking for r at 5.4. We want to get an estimate of that. And they want us to use the tangent line approximation. So we want the tangent line approximation at t equals 5. Tangent line approximation at t equals 5. Okay, so tangent line makes us think of slope and makes us think of derivative, right? So tangent line, slope, derivative. That means we're going to be doing r prime at 5, okay? So this is the slope of the tangent line at t equals 5, right? R prime 5. Now that should be equal, since we're only doing approximations here, so that should be equal to r at 5.4 minus r of 5 over 5.4 minus 5. Now you might say, why can we not use 5 and 7? Because earlier I used 5 and 7. No, you don't want to use 5, no, you don't want to use 7. You want to use the 5.4 because you're actually looking for that 5.4. You want to look for r at 5.4. So you want to see an r 5.4 in your equation. Okay, look at this equation again. It's just the slope, right? So we are now going to simplify this. You're going to have r prime at 5 equals r of 5.4 minus r of 5 over 5.4 minus 5, which is just 0.4. Now multiplying both sides by 0.4, you will have 0.4 times r prime 5 equals r 5.4 minus r of 5. Now since we're looking for r 5.4, I want to leave that on the right side of the equation. So I'm adding r5 both sides. I'm adding r5 both sides. And so we come up with r5 plus r prime of 5 times 0.4, or 0.4 times r prime of 5. It's going to be the same thing, equals r of 5.4. Now if you look back to the scoring guidelines, that is actually how they wrote it, but they did not tell us how they got into that equation, right? So hopefully you understand it better since I started with the slope formula at the beginning, the r prime 5 here. So if you look at the scoring guidelines, it's now r 5.4 equals r of 5 plus r prime of 5 delta t. Now your delta t is just the change of time from 5 to 5.4, which is actually 0.4. Okay? Now, the next line would be, so now we already figured out how they came up with that equation. It all came from the slope. Now, let's move on to the next line, which is to put in the values. So r 5.4 equals, now your r5 from the table will be, oh no, not from the table, from the initial value. R5 is 30. If you go back to the beginning, to the problem, it says the radius of the balloon is 30 feet when t equals 5. That's an initial value, and I pointed it out to you earlier, right? So R5 is 30, that's from the initial value given, equals to, because that is the r prime, the value of r prime at 5. If you look at the table, you're going to see it there, that r prime at 5 is 2, times the delta t, which is 0.4. That's a change in time from 5, t equals 5 to t equals 5.4. And so, simplifying that, you will get 30.8. And you have to put the units there. The radius is in terms of feet. Okay? From the table, you can see that r prime is feet per minute, so that means the radius is in feet. So you get a point for this, for the estimate, using the tangent line. And then you have to give your reason, your justification for that. Now, we are given that the graph is concave downward. So graph is concave down anywhere. It's concave down on the interval. Anywhere on the interval 0 to 12. So you can put your reason now. Since the graph is concave down on the interval time 0 to 12, then our estimate, or the estimate, is greater than the actual R 5.4. Our estimate is greater than the actual one. Now you might say, why is it greater? It's because if your graph is concave down, so I'm gonna draw a sketch of that. So let's say your graph is concave down, so it's gonna be facing this, it's gonna be like that, right? The curve would look like that, concave down. So anywhere you are, your tangent line will always be above the graph, right? Anywhere you, at any point there on the graph, if you draw the tangent line, it will always be above the graph. So the tangent line is always above the graph. And since we use the tangent line as our approximation, then naturally the value that we got will always be greater than the actual value of the function. I don't know if that makes sense. Hopefully that makes sense. Since we use the tangent line as to approximate the value, then our approximation value will always be greater than the actual value, because the tangent line is always above the graph anywhere in the interval. Does that make sense? Okay. If you have comments on this, hopefully you learned something from this. If you have any questions, then just email me. Okay? Bye-bye.